A brief about CloudX Lab. CloudX Lab is essentially into an online education, in an online education, and we are trying. And I am Sandeep Giri. So the format of the webinar today is that we will take questions, and I'll be asking questions to Professor Dimitris Angelakis. And Professor Dimitris Angelakis is an experienced research professor in quantum physics. He has a PhD from Imperial College with several years of research experience and leading research groups in Cambridge University, Greece, and Singapore. And he's demonstrated world-leading research excellence in quantum simulation and quantum computing. Recipient of several awards, including 2018 Google Computing Innovation Award for his work in quantum simulations. His work has appeared in Science, Nature, New Scientist, Nature Research Highlights, the Innovation Magazine, Physics World, CNN, and Sky, amongst others. Over to you, Professor Angelakis.
Thank you, Sandeep. Thanks for the invitation. Glad to be here, and good morning to everybody on this side of the world in our time zone. Good evening in US and Europe. You know, as you said, we're living through difficult times. I prefer talking to live audiences. It's much easier to communicate and interact, but maybe there is an advantage here as well. We can reach more people. So today I will give a very, very basic introduction in quantum computing. This is by far not aimed at specialists. So bear with me in that case if there are some things you've already heard. And we will start by introducing the field and also our group and our center here in Singapore. So as Sandeep said, I'm a principal investigator and group leader in Singapore Center for Quantum Technologies, and I'm also an associate professor in Technical University of Crete, the School of Electrical and Computing Engineering. So we're living a quantum computing race. You might have heard about different ways to make a quantum computer. I will talk about superconductors, about photons, about ions, exotic systems, quantum systems that can basically allow us to build a quantum computer. It's on the news very much the last 2 or 3 years. You hear about quantum computers about to get real. You hear about the work at Google and quantum supremacy. You hear about commercialization of quantum technologies and a lot of startups and smaller companies that are trying to kind of compete with the race with the universities and the big ones. So let me kind of try to tell you a little bit about where we are. I will talk about the prototype quantum computers at the moment, which are existing, small and noisy, but a few dozen of quantum bits at different level of controls by different companies and institutions and spin-offs. And I would like to tell you basically what is real, what is hype, why we care about quantum computing, how we think it's gonna work. And the last one, the when, should actually have a lot of quotation marks here, because this is, I think this is the most important question, I guess, for most of us at the moment. I will start by telling you a little bit about Center for Quantum Technologies and our group, where we are globally in terms of quantum technologies, what's the state of the art, and what is quantum supremacy, which can dominate the news the last year or so. Roughly what quantum computing is. This is very, I don't expect in a Saturday morning and 1 hour talk to really cover the whole field, but we'll give it a shot. And I will also mention potential industrial use cases in machine learning, optimization, and chemistry using what we call hybrid quantum classical approaches. And I will end with the quantum hardware, basic principles, how does it operate, and what's the state of the art. Sandeep, are you there? So I just want, you can all hear me, and so it should be fine. Can you see my cursor, Sandeep? Anyway, so what's Center for Quantum Technologies? Center for Quantum Technologies is what we call a national research center. It was initiated in Singapore 2007. And basically, it's a research center focused in quantum technology. That's what we do here. We have different people from different backgrounds, computer science, quantum physics people, theorists, experimentalists, all under one roof, housed in the National University of Singapore. Roughly 200 people. This number is fluctuating, but on average, we are 200 people. It's 20 group leaders like me, and we have a lot of PhD students, visiting professors and staff, and an excellent admin team. And our current chairman is Mr. Quek, and director Professor Eckert, and Professor Latorre will take over soon. So CQT was established, as I said, 12 years, 13 years ago. It's mainly funded by the government, the Ministry of Education of Singapore, National Research Foundation, and as well as the universities, and also external grants. What we do quantum computing, quantum communications, and quantum-enabled devices, roughly. We do basic science, but we also look more recently quite a bit on downstream and applied things, but our mandate is to do fundamental science. So we look at optimization and simulation. This is the things I'll be talking about a little bit more. We have a lot of activities by colleagues in quantum communications and quantum key distribution. And we also build devices of different types, like quantum sensors and quantum clocks. This is our group, just to give you a bit of a background on what is happening in my group. As Sandeep said, I did my PhD back in England almost 18 years ago. Then I was a researcher in Cambridge for a few years, and then I moved to Singapore and Crete in a macroscopic superposition for the last 10 years or so. This is some of the group members. Without them, nothing would have been possible. They are basically the people doing all the hard work and all the nitty-gritty calculations. We have some collaborations as well with external universities, and also with some hardware providers like Google, for example, which I'll mention a little bit more. So what we do, and before I start the introduction to quantum, is our more kind of applied version of or downstream research is about applications of quantum computing and quantum simulation, where we have kind of in the next maybe 2 to 5 years, even maybe even more, we will still be using classical computers, that's for sure. And we're going to have a hybrid type of approach where a classical and a quantum device are kind of talking to each other. You'll be using a quantum computer to prepare exotic quantum states and measure them. And then you use a classical computer to either pre or post process and do some sort of optimization approaches there. And this is how you basically the first kind of more near-term algorithms are looking like. There is a lot of pros and cons in this approach. I'll talk a little bit more about it. The pros are that there's something we can do with noisy quantum systems, with small prototype quantum computers. The cons is that in some cases, you can't really prove always that your quantum algorithm will always be faster or better or have what's called a quantum advantage compared to a classical case. But however, this is something that is very, very close to what a lot of applied groups or companies are working on. And we are also kind of looking at this very, very closely. One example of our research work, this is more upstream and basic research. As I said, we're a theory group, so we do quantum algorithms and quantum physics type of approaches. That's how we spend our day. And one kind of recent collaboration was with a Google hardware group where they built this. This was the 9-qubit chip. There are 9 qubits here. This is superconducting wires. Everything is, I'll talk about it later, is cool, very cold, put down at almost 0 degrees, absolute 0, a few millikelvin above absolute 0. And then you can actually manipulate these qubits, the superconducting circuits, and do some useful computations. In our case, what we did was called an analog quantum simulation, where we use this chip to understand how electrons behave in complicated materials in the presence of disorder and interactions. So that was published a few years, 2-3 years ago. So let's get into the main part of the discussion today. Quantum computing 101, why, how it works, and roughly. So why go quantum? As of September last year, roughly, we all know we're producing massive amounts of data every day. It's not only the size, of course, but I'll get back to this later. But just to give you a feeling, this is roughly 250,000 libraries of Congress or 5 million laptops. That's daily. This is a lot of data. Every minute of every day, we have billion internet users feeding the data banks with hundreds of thousands of tweets, of Facebook likes, plus all the other data we create by taking pictures and videos, saving documents, opening accounts, and more. So the question is, can we cope with this exponential increase in the amount of data we produce? Can we process and can we make sense of what's going on? The tools we're using so far, classical computers, to process information, basically suffer from what's called the Moore's law. So roughly every couple of years, we all experience this. You get a laptop today, then 3-4 years down the line, it starts dragging, and you need to kind of replace it because it just cannot cope with the new progress and the new kind of size of problems that are thrown into it. The idea was that speed doubles every 2 years or so, and the same sign, the chip size, the transistor size, or the numbers of transistors you can put on the chip doubles, and the size becomes smaller and smaller. So this is kind of projection. If you go back to the 90s or the 2000s, for the more kind of senior of us, I did my PhD in a Pentium 2 20 years ago, Pentium M, Pentium 4, this kind of era, the early 2000s. That was roughly, in terms of the feature size, at the 0.1 micrometers and below. 25 nanometers, or maybe a bit less these days, but that order of magnitude is the limit to optical lithography. We can't get smaller than that. And I mean, this slide is a bit old, but we're already kind of hitting this limit. This is where the feature size becomes, few hundreds of atoms across. This is the quantum regime. This is as kind of trying to be put in this recent movie, The Ant-Man. You're getting in a very weird world of atomic and quantum physics. We just cannot control circuits and switches and connectors the same way that we do in the classical world. So there is noise. The simple way to put it is that there is noise and things basically do not work. So on the other hand, quantum effects can also provide a solution here. And that's exactly what quantum computing is about. So this is also seen in the performance. If you look at this supercomputer speed, here I'm plotting the top development for the last 5-10 years. This is number 1. This is the number 500 in terms of speed and performance in the world. This is the sum. And this is in terms of gigaflops, teraflops, petaflops. As we go on in the decades, we see that we're reaching a plateau. I mean, if I had put this a bit of old slide as well by a colleague, you're hitting this horizontal plateau here. We just cannot get more power out of the current machines. So we can't get below this 7 nanometers. A feature shower is very difficult to increase the number of cores when we do large scale computing. We're producing a lot of heat and power, so we have to do something else. And what is something else? I mean, there are many possibilities, but that the most kind of promising one at the moment seems to be quantum. First of all, quantum computing is far from anything you have encountered before. We have encountered in kind of human history and human civilization. And one kind of simple example to see that is you have the abacus, you have one of the fastest, maybe the fastest supercomputer in the world now, IBM Summit. These two things, although they look very far apart in history and in speed, actually they're very similar devices. The way the calculations happen here and here is exactly the same. We count one by one, we add numbers, we subtract numbers. It's just that this guy on the right-hand side does it much, much faster. Trillion times faster than we can do by hand in this ancient Greek or ancient Babylonian type of device. So quantum computing is very different. Quantum computing exploits the natural state of atoms, electrons, and nature to process information. So, and kind of what we have a feeling of is that it does that in a parallel type of way, in a massive parallel processing way, but we don't really understand it. Nobody understands quantum physics. So we have a new kind of science the last 100 years or so. I mean, the science, quantum mechanics is 100 years old or more, but the 21st century will be dominated, and is getting there already, by what we call quantum information science and technology. Will be the merging of these two seemingly different areas for the last century, the 20th century, and we're getting into this new merging at the moment. We all know that quantum physics was there already, also in parts of our technology. Classical computers, the way we're communicating now, the way you can see me and I can see you, and discuss with different parts of the globe and different electronic devices and applications in medicine. These are still based on quantum physics, but they're based on a different aspects of quantum physics. It's the quantum physics of the many particles, of the wave nature of electrons and atoms, but at the level of having lots of them kind of inside the material, and specifically in semiconductors. So this is not what we're talking about now. For 21st century, what we're talking about is the ability to go inside at the nanoscale, at the atomic scale, and manipulate quantum particles, quantum entities one by one, and control the way they interact and what we call entangle with each other at this microscopic or nanoscopic level. This is the key difference. And in this case, entanglement and superposition is two very important notions that will dominate the language of science and technology the next during 21st century. So let's do quantum mechanics and quantum computing in roughly, what's the time, maybe 10, 15 minutes. I know it's a bit of a challenge, but we'll give it a go. Two disclaimers by two fathers of quantum mechanics. Anyone that can contemplate quantum mechanics without getting dizzy has not understood it. And it's safe to say that nobody really understands quantum mechanics, you just get used to it. I think both are very, very close to my also very small experience the last 20 years or so with quantum physics. You just take it because it works and it explains nature. So let's go and talk about information and atoms. I mean, information is in two states. You can have 0 or 1, and you can have, let's say you have an electron circulating a nucleus in an atom. I can take one orbit to be my 0 state, and I can take my other orbit to be state 1. So this is, anything that has two distinct states and two possibilities can be done like this. In this case, usually in computers, we have having or not having a current going through a circuit, or we can have a small magnet pointing up or pointing down. In this case, we have two atomic states. So this is all fine. This is still quite classical and quite clear. We take 3 of these atoms. We have the electron circulating in a specific orbit. Then we have 0, 1, 1, for example. Let's put now these electrons in a superposition, as is possible in quantum physics. Putting electrons in superposition has been done numerous times in many quantum physics experiments, but let's see that now from the information perspective. If the electron is circulating in both orbitals at the same time, if it's put there using some quantum physics experiment, then the corresponding information, or the memory slot, if you want to see it, different ways to look at it, it's also in some weird superposition of 0 plus 1, 0 plus 1, 0 plus 1. But what does this really mean? I mean, it's very difficult to understand it. One kind of classical trick that our brain kind of plays when we see this kind of magic images is this kind of question where you have two possibilities, two pictures at the same time. In this case, there's an old woman with her face turned on the side, or a young lady looking on backwards. So, and the question is, which one do you see? If we make a small statistics experiment now, probably 50% of the people will see one, another 50% see the other. And if we look at it for a little bit longer and allow our brains to play with the foreground and background, we start seeing both. I mean, but again, this is a classical analog. This is nothing to do with real quantum superpositions, but it's a very interesting picture just to have in mind. This happens at the level of nature, at physics. This is possible. The electron actually is at two possible positions of existence at the same time, and this is how experiments basically get done and have been verifying it all the time. If we put that into computing, then you can start seeing some possibilities for some sort of parallel processing. There's more to it, as we'll have these superpositions with 3 slots. You can have 2 to the 3, 8 possibilities. So if you could actually do some sort of computation here, processing, information processing on the input, then you can somehow extract that power that is hidden down there at the quantum physics level. Again, this is very rough and very, how to say, almost inaccurate, because there is more to it. If you look at this a little bit more and think for 5 minutes, you will come up and say, okay, well, I have a superposition here. I'm measuring this. I'm doing some sort of parallel processing. I'm calculating the function values of all the 8 possibilities. But then when I'm here and I measure, I only get 1, because that's what the classical world is. When we make a quantum experiment, when we open the box and we look at the poor Schrödinger's cats, for whoever of you have heard the paradox, the cat is either dead or alive. It's not both. So how does it work? How can I really do something useful out of this? Well, the key is you have to explore what's called quantum interference and getting some of these computations to cancel each other out or possibly constructively interfere with each other, such that the answer here, the answer that you are looking, the useful answer, is surviving the computation, and all the wrong ones are destructively kind of canceling each other. And I have I think it's further down. Just give me 1 second. Yes. So it's basically computing via quantum interference. So if we want to see a little bit of a model here, imagine that each of these states is a possible computation. So I go from one initial state with some probability amplitude to another one, and another A2 is another kind of way to end up at this answer, or I can go this way, or I can go that way. This is like light going through some sort of optics experiment, you can imagine. So quantum algorithms work in a very similar way, but if you go A1 and then A2, or A3 and A4, if these A1s or A2s are complex numbers or waves, then you have this extra phase factor, as we call here, which plays a big role in ending up in any of these possibilities. It's a little bit technical now, but I won't go. This is the only question that there is in the talk, just to give you a feeling what's happening. We can play with these paths and the phases of these quantum waves that are interfering when we design a quantum algorithm, and we can get the output possibilities such that this is the solution, the right solution. All the wrong solutions are kind of destructively canceling each other. This is different this is a note for the classical computing experts in the audience. This is different than a probabilistic Turing machine, where you have different probabilities and you add them up. In this case, there's no phase factor that can cancel each other. The probabilities always add up, not in quantum amplitudes. In quantum amplitudes, probabilities can also cancel each other. So let me go back to the what that allows us to do. So in principle, if you have 5 qubits, you have 2 to the 5th 32 states. If you have 9 qubits, you have 512 possibilities, and so on. With 35, you're already just writing down all the possible numbers and storing them in a memory, classical memory kind of resource. It will take you 4 gigabytes of RAM. If you have 50 qubits, that will take you 10 to the 15 states. And this is close to what supercomputers basically can do and process these days. And this is also the limit to quantum supremacy, as I will explain later, that has been achieved. With 300 of them, you have more possibilities than the number of atoms in the universe, basically. So there is a lot of hidden power there. There's a lot of hidden possibilities. However, it's not as trivial as in this very simple slide to design quantum algorithms that exploit this. As I explain later, you have to really figure out how to do the quantum interference such that the right answer comes out and it's enhanced. So this is probably a good point to stop for a minute. I don't know if there's any questions at this stage before I continue. Sandeep?
Great, great. So there are quite a few questions I myself am having, and also users asking. So quick question is that when do you think we will have an operational quantum computer? Will those be useful?
Yes, this is a very good question. I would leave that to the end, but let me give you a projection. I think when I talk about the hardware and the race and the milestones achieved the last few years, it will be clearer. I think it's a very how to say, it's the question in the field for sure. I think we're going to have devices that do certain things very soon, very specific things like in the 1950s or 60s, but a universal quantum computer that does everything, it will be years away. I would say more than 10 years away, at least, the way the technology goes. But give me a few more minutes and it will become clear when we talk about the hardware and where we are. Like at the moment, we're between 50 and 100 qubits in the hardware. And algorithmically, we're still far from that, but we have quantum supremacy, which is achieved. Okay, so let me tell you a little bit more about one or two slides on the mass of quantum computing, very, very basic, and quantum mechanics. The superpositions, we basically write them down in this weird exotic language using Dirac notation, where a quantum state can be superposition of 0 and 1, where alpha and beta are complex amplitudes, which if you square them up, a squared plus b squared is always 1. The probability of finding your qubit at state 0 is a squared, and the probability of finding your qubit at state 1 is b squared. And what quantum mechanics allows you to write things like 0 plus 1 over square root of 2. So this state is impossible to envision, to realize, or to do classically. This is the key difference. The basic mass of quantum mechanics are not very hard, at least at the level of qubits. Of course, there's much more to it than this simple picture. And basically, you can imagine that qubits live in a sphere. We call it the Bloch sphere, and they can actually point in any direction in this possible kind of three-dimensional sphere. Classically, a bit can only point to the North Pole or to the South Pole, where a quantum bit can be anywhere. And they are very, very specific and reasonably simple mathematics that explain all the possible states that the qubit can exist. It doesn't explain how quantum mechanics work, but explains you how to manipulate bits at this simple level. And how to do gates, for example, how a NOT gate flips a qubit from 0 to 1 or 1 to 0. This is also there in quantum, but there are also these exotic gates, which are matrices again, plus another case, which they can do superpositions. This is kind of like a half NOT gate or a square root of a NOT gate. So you start from 0 and you go halfway through. This is impossible in classical computing. That's very, very kind of just to get a taste. Okay. So in parallel to the circuit model, we have qubits instead of bits. We can prepare those qubits as inputs to the machine. We can do 1 and 2 bit logic case. Here we call them unitary transformations. You can go backwards in time in some way. In quantum computing, everything is unitarily. And then you have some sort of readout process, and you have external control by a classical computer. The classical computer tells you what kind of signals to send to your device to make the gates. I'll talk about it a bit more in in the hardware part. And this is some example of some of those gates. This is the X gate or the NOT gate, and this is how it looks like a matrix. It flips a qubit, but there are also these other ones that are not there in the classical computing. The Hadamard gate that creates superpositions, phase gate, and control gates. There's a lot of work recently in developing, higher level languages that one does not require to know full quantum physics in spending 5 years doing a PhD to kind of program and play with a quantum computer at a high level. IBM has been doing a lot of work. Some of you might have seen it, and also other companies. Google has just released Circ and other higher level type of programming languages for non-quantum people that want to play with a quantum computer. These are also kind of available online these days, and that's quite helped to open up the field to larger audiences. So let me go through this. I've already explained this. So let me give you an example of an algorithm now, which was the first, probably historically the first one as well, that does something more than a classical computer. Let's say we have a coin. In this case, this is a Singapore dollar coin. It has a head and it has a tails, and somebody tells you, tell me whether the head, like the two sides of the coins, are the same or different. Don't tell me which one is which, but tell me whether they are head and head or tails, or the coin is fair. To do that, you need to look in one side, register the answer, turn it, look, register the answer there, and then compare. In terms of mathematics, this can be mapped to what's called calculating, computing a function from one bit to one bit, and then comparing the values of the function. So if f of 0 is equal to f of 1, means that two sides are the same, or if f of 0 is different than f of 1, the two sides are different. So the task is whether f, the function, is constant or balanced. If this is guaranteed by the problem, if somebody tells us that this is the case by defining the problem, then we can, classically, you need to do it twice. You need to evaluate f of 0 and f of 1 and compare and see if it's the same or different. Quantum mechanically, you can only do that actually using the oracle, as we call the black box, only once. You don't have to do it twice. And how is that possible? Well, it is because you can actually put the input in a superposition. And this is, I mean, I don't expect you to understand fully now the circuit, but I'm just going to show it so you have a feeling how the maths look like. So you start with, this is your classical black box. This is the quantum black box. Now your inputs here from bits become qubits or quantum states. This is your unitary transformation that does the oracle. This is the output. So this kind of the black box we design here outputs this z addition modulo 2, the value of the function. And we do the same thing here, but we encode everything in quantum bits. Now, if we run this once, in classical computing, we have to run this twice to get f of 0 here and f of 1 and read the output. Here, we'll see that we can do it in once, and with 100% probability, the algorithm works every time. By looking at the output, we can tell whether the function was balanced or, constant or balanced. The algorithm works like this. I won't explain the math. It takes a bit longer than an hour to understand it, but not much longer. Maybe a few lectures. So we start with 0. We go to 0 plus 1. And then we do something what's called putting the information in the phase of the qubits. So the 0 and the 1 carry this phase factor, which can be factorized out And depending the value of the function, by looking at the output here, after we finish the interference, these Hadamard transformations are basically interference devices. We put this into superposition like a beam splitter in photonics. We do the calculation, and then we close the superposition here. We close the circuit. By looking at the output here, if we get 0, then we know it's constant. If we get 1, we know it's balanced. This is just a very simple kind of and very important algorithm to study the field. I mean, again, I'm not expecting you to understand everything at this stage, but just to maybe you can keep the kind of the terminology a little bit how it works. There's more to it, of course. Another application that kind of started the field, very famous algorithm, was the Shor's algorithm. Peter Shor, almost 25 years ago, mid-90s, came up with algorithm to factor large number in a quantum computer in almost polynomial time compared to exponential takes classically. So if I give you this very, very big number with red digits here, this is 100 digits or more, then if you want to find out what are the factors, factorize this number, these are the two factors, it takes you a long time, lots of steps in a classical computer. So, however, if I give you these two factors, it's easy to get this number. You just multiply and you get this number. So what Peter Shor showed that if you take now what's called cryptographic algorithms, RSA encryption-based algorithms, which are kind of work on similar type of principles, you're using factorization to encode information. And this is something we use nowadays technologies. If you try to crack this using a classical computer, and this is the key, how big your key in this encryption algorithm is, 453 bits. For example, this was cracked back in '99, and it would take you 10 CPU years. This is how much time or work 1 gigaflop machine, like a older laptop in some sense, would take you to crack this number. If you have it, let it working for 9,000 hours. So it would take 10 of these guys, 10 CPU years to crack this. And of course, this was done 20 years ago, not on a laptop, but on a larger computer. So Shor's algorithm, if you have roughly 2n plus 3 qubits, let's say around 1,000 qubits, it would take an hour, assuming that each of the gate takes you 10 nanoseconds. You make bigger keys, it's harder to crack, and it's actually exponentially harder to crack. It took another 10 years, and you see that in normal years, human years, and in CPU effort, from 10 CPU years, you go to 2,000 CPU years. And you go to 2024, you get 1 million CPU years. Where in Shor's algorithm, you go 1, 5, 10 hours, you go polynomially. So this was kind of the big wow kind of instant of the field, where everybody kind of start paying attention to quantum physics beyond just as a upstream exotic physics discipline. Of course, the algorithm, the maths, and the hardware, there is a gap. We need to do this, we need 4,000 or 10,000 actually fully controllable, as we call topologically protected qubits, error-corrected qubits. And that's very far from what we have now. You mean millions of physical qubits and hundreds of millions of gates. This is not, unfortunately, possible at the moment with the technology we have. Due to the extreme hardware requirements, there's no physical reason why this is not possible. There is no no-go theorem or physics forbidding law that we cannot do that. It's just that the technology is not there yet. And we need to kind of have paradigm shifts to get there, but it's, you know, it's happening. So what, just as a kind of a side joke, I call this a little bit Star Trek quantum computers, if we want to do that. However, there are closer to our current times devices that can do certain things. And this is what I want to talk about now for the rest of the talk. What are the possible use cases with near-term devices via this hybrid quantum classical approach, where you have your noisy prototype small quantum computer of a few hundreds of qubits, maybe a few thousands, noisy and kind of physical qubits, and then you do some hybrid computation, combining both classical and quantum to solve realistic problems. So I will talk about 3 use cases. I'll talk about quantum chemistry, about optimization problems, specific quadratic optimization problems for logistics, financial portfolio, shipping and delivery routes, and also applications in machine learning for learning data and predicting behavior, like one example is generative modeling. And these approaches are both digital and analog based. And so before I move into this part, maybe I can take a couple of questions if there are any, Sandeep, or should we?
Hi, so yeah, there are a few questions that I want to just bring it up. I think, let me just walk through the question. So first question, I think that you will be covering in and the rest of the session is that is quantum computing method going to help the AI world, or is quantum computing? I think you are going to cover this question later, right?
Yep.
Okay.
In machine learning, yep.
Okay. The other question is that are there any examples of quantum computing that can be experienced now?
Yes. I will also talk about, I mentioned it a bit earlier, you can go online in the IBM Q cloud access and access a 5-qubit quantum computer for free. There is a queuing time, and there is a simulator as well, and you can use basic programming tools. Let me show this slide that they provide that called Qubits to program this quantum computer. So you have this is how the circuit looks like. You have 5 qubits, and you can put your control nodes, your node gates, and so on, and then run the circuit and measure and get an output. And there is instructions there to play with very simple quantum algorithms as well, like the Deutsch algorithm, which I just showed about the coin, and also more advanced ones. So that's there. Of course, it's a tiny 5 qubits. There's not much you can do, but it's amazing as well that even in my kind of lifetime, 20 years ago, to access 5 qubits, you had to be in a top research lab in a top research university to do that. And now this possibility is out there, and it's possible. There are other providers. Google is not offering access yet, but they will probably do soon. There is other companies like Rigetti, spin-off from Yale, and a few others that Amazon is coming into the game as well. And I will talk about the companies a bit later, actually. So the answer is yes, there are possibilities.
Wonderful. So far, I mean, the audience are really liking your presentation. People.
Thank you.
It's very good. So far, it's going very, very great. And there is somebody has asked a question like, is D-Wave computer a quantum computer?
That's a very good question. I'll get about the D-Wave later on. Let me give you a short answer now. We are very far from having thousands of proper quantum bits as D-Wave's claiming they have and controllable. The academic community is looking at what they have very closely these days. They do have performed certain calculations and tasks for very specific problems, I mean, a small area of problems, especially in optimization, with some very exciting results. It's not very clear if it's fully quantum or it's just normal classical annealing, as we say. So the community's perspective is that it's not a full quantum computer. At least it's very different than the quantum computers I'm talking about here now. So, but I'll say a few things later.
Okay. This very interesting question by Ray. Question is, how small can quantum computers get in the future? Will it be the standard in the size we have the computers right now,
Yes.
or maybe handhelds?
Let's answer that at the end as well. At the moment, quantum computers are very big. They are big as they're atomic physics labs, basically. I will show some pictures later on. So from that side to this side, it will take some time. We're like in the 1950s where computers were taking full floors to operate. Okay, so let's talk about use cases. The first use case I will talk about is quantum chemistry. This is one of the possible short-term applications where you have complex simulations of chemicals and materials. Actually, 1/3 of supercomputing time these days is spent on these simulations. There are designs that can never be done classically that are predicted to be solved with a few hundred qubits. They're used for pharmaceutical and medical simulations, and also in high temperature superconductors research, where has application to energy transportation, for example. If we can build wires that do not lose energy when we transport electricity, it will be a huge application. Doing that requires a lot of computational power and computation that cannot be broken down or parallelized. And even making fertilizer is something which is very, very hard. And it sounds very simple, but it's actually very important. It costs 3 to 5% of the world's natural gas production goes into this. And designing catalysts that simulate the bacterial reactions, we feel, and there have been works by many different groups in this kind of chemistry direction, that 100 to 200 qubits could do much more than we can do with classical computers in using this variational hybrid quantum computing approaches. And this is something that, because of the qubit requirements, could be done the next 2 to 5 years. I'll skip the mathematical slide. This is how it works, and just give you a feeling of what we expect we'll be able to do. With 2 qubits, you do small molecules, to hydrogen-2, or lithium hydride, or beryllium hydride, 6 qubits. Then as you go on the number of qubits, you start doing more complicated molecules. And we hope that we might be able to do iron sulfur, which is very important in certain other substances, and even go towards proteins, which is this is the holy grail. If we can understand how certain chemical reactions happen at the protein level, protein folding as well, so it's a slightly different thing, then we could do dedicated drug design, which is very, I guess, very important now during the COVID era as well. We can simulate how certain drugs act on the body at the cellular level, at the protein level. It would be very important. So we are roughly, in terms of hardware, in this regime, and this is kind of the time scale or the qubit scale required. So we don't need millions of qubits in this sense. Well, maybe with a few hundred good qubits, with low noise qubits, things can be useful things can be done. In another direction, in quantum AI and quantum machine learning, there are a lot of applications in looking for patterns in classical and quantum data and learning distributions. In one way to categorize machine learning type of field, you look at the type of the algorithm and you look at the type of the data. If you have classical data and you use classical algorithms, we're in this corner here, and this is where basically classical AI is, from neural networks to clustering and classification, for market research, for prediction, for forecasting. This is all classical AI, basically, and machine learning. We are entering this area where we know, I will give some examples, that we have quantum algorithms to do classical data and do them very well and do them faster as well. And on the other hand, there's quite interesting work in doing classical machine learning to understand quantum experiments and optimize the way we set up our labs as well, process our measurements and process our data. And this is another exciting area. And in this quadrant is where you have quantum algorithms looking at quantum experiments as well, and this is something that is being evolved. Now, the indications are that the more exotic the distribution here, you have classical data that are very, let's say, spiky or complex in terms of the structure they have, the better the quantum approaches can do. However, there is a catch in terms of big data and large data. We don't know yet how to do what's called a quantum RAM problem, at least experimentally. I mean, most of these algorithms, I'll talk about it later, they require you or assume that a quantum RAM is possible. This is something we don't know how to do yet. And that's a catch. And also, we don't know if you have a lot of data, like petabytes or something, you still need to read them. You still need to load them in the machine. And this is a bottleneck. But however, there is a lot of activity in this area. We see that AI and training a neural network to give you a feeling takes days, sometimes consumes energy as big as a small town, produces a lot of heat. So there is a lot of efforts to come up with alternative methods to do this using quantum algorithms. There are many areas that are being pursued these days for quantum clustering, quantum support vector machines, quantum principal component analysis, feature topologies, and quantum deep learning. These are all areas that are very active these days at the theory level and algorithmic level. Again, one has to be careful with the hardware requirements and whether you need a quantum RAM or not. This is kind of a categorization. What can be done without a quantum RAM or with a quantum RAM? And this is the algorithms. So for example, if we look at quantum neural networks, a quantum Boltzmann machine will have exponential speedups. A quantum neural network that works like as a Boltzmann machine, that's for the specialists that know what a Boltzmann machine is very good. It doesn't require a quantum RAM. It has some other issues, but it doesn't require this quantum RAM. Or where, for example, the quantum support vector machine, which is something I mentioned here in briefly. I don't want to go too much details now. It's too much to cover in one talk, where you're trying to find a hyperplane that separates two data sets. This can be done exponentially again, but it requires a quantum RAM. So it's tough for us to implement it at the moment. And there are other cases, as I mentioned, there's online perceptrons, Bayesian interference, quantum reinforcement learning, and so on. This review is a good reference to have a look if you are a machine learning expert. And I will end with two more use cases in optimization and logistics, in energy management and in financial portfolio optimization. And of course, there are many others in shipping or delivering routes, in plane gain allocation, and anything that has to do with optimizing over many possible different possibilities. So in energy management, we know, for example, that quite often you have a lot of different energy sources. You can have your renewable ones like wind energy or solar or hydro, and or you have your more classic ones like diesel based, and you want to basically put this all together at the country scale or even at the continent scale sometimes, and design an efficient management system such that you store your energy when you don't need it, you use your renewable ones optimally and put them at optimal locations as well, especially in terms of distances, because you have to kind of transport the energy also. And all this has to be done in an optimized way such that you get the maximum energy output at lower cost. It's a very hard problem. It's what's called a hard quadratic optimization problem, combinatorial problem. And that's very hard for classical computers. Just to give you an example, one is you have your facilities, your factories. Where do you put your facilities in terms of distances and optimal locations to transport the energy to the user as well, minimize facility opening and transportation cost for given energy demands and resource availability. That's called the facility location allocation problem. So this is something that can be done efficiently, and this is where D-Wave comes. We mentioned it earlier. It's one of the early demonstrations of some of their works. But this is also possible now with noisy, these variational small quantum computers, and some results are coming out as well. Very, very briefly, what has been shown here is that as you increase the number of facilities, all the possible combinations, and you're trying to find what's called the lowest possible value of your cost function, this is the best known solution in this kind of specific problem. This is a number that basically has to do with, let's say, the overall cost or the overall minimization cost value that you need to kind of identify in this case. The closer you are into this value, the better you are. As you increase the number of facilities, that kind of cost goes up, but the time to get that objective function, when you do all the possibilities in a classical computer, grows very, very fast. It blows up from 9 to 12 to 14. You just, this is how long it takes you in a classical CPU core as a function of the problem to get to the solution. And over here, there's no data because it just explodes. It just takes too much time. And people have run this in some prototype D-Wave quantum annealers, I would say. I wouldn't really call them quantum computers exactly, with some where you can actually get the minimum of this function quite fast. Now, this is also possible, as I said, in this 50 to 100 qubits variational quantum computers, and lots of people, including us, are designing algorithms to run them in different hardwares provided by different hardware providers these days, including Google, Rigetti, IBM, and so on. Of course, this is very attractive for governments and companies. There's a lot of investment recently in this energy management type of applications, and of course, chemistry and materials research. Now, let me also talk about the financial optimization problems a little bit, very briefly. Again, each of these things are a field by themselves. It's an area of research, applied and upstream research. In financial portfolio optimization, questions are: what assets should be included in an optimal portfolio? How should the composition of the portfolio change according to what happens in the market? How to detect opportunities in different assets and take profit by trading them? And how to estimate the risk and return of portfolio or even a company. So in this case, you have given is a set of equities and a target return. You need to find you have to allocate to its equity that minimize the risk. And there are different strategies. You can hedge, hedging or diversify. What to do is basically could go in any direction between the two. So you can actually model some of these problems, writing down a cost function again, or a return function as it's called, which we put the risk, the transaction cost, temporary and permanent market impact, and you can put variables here that model the problem as a quadratic problem. This is W here, W squared. Very briefly, I don't want to go into details here. And the idea is to, for given values of this constants or coefficients that describe the risk, the cost, and so on, how to optimize this. This is quite hard, again, in a classical computer. It takes a long time. And we do have a lot of theoretical algorithms at the moment that has proven that this is possible to do much more efficiently. And there's this ongoing work by big banks collaborating with some researchers like us and institutions and hardware providers to solve these problems. And I will end with this quantum supremacy discussion, what has happened recently, where we are basically in the field in terms of state-of-the-art applications and the hardware. So back in September, October last year, there was very big news, kind of dominated the media, that we reached quantum supremacy. Quantum supremacy, it's a slightly unlucky choice of term, especially in the West. But anyway, it's here to stick. What is defined basically is defined as a well-defined computational task, a well-defined problem that a quantum machine can outperform a classical machine. But when I say well-defined, there's a lot of fine print there, like something that you could write down very specifically based on the resources you're using in the quantum machine and a classical machine and compare. This has been going on for many years in the field, and it has started by some pioneers. John Preskill coined the term a few years ago, and a few others have worked in this area, Scott Aronson and many others, trying to quantify how to do it. And Google basically had it in one of their, another groups, in one of the kind of important milestones to achieve. And according to them, and according to most, I think the community has accepted it now, this is published, this has been achieved. So I will say a little bit what it is. Using a 54-qubit superconducting processor, basically a complex quantum state has been produced in 200 seconds that it was kind of impossible, or if you project out, it would take a classical supercomputer 10,000 years. Of course, there is big news here. There's a little bit of hype in the media as well. We have to say that the experiment is true. It was a milestone. However, the computation is not useful for any real world problem. This is a mathematical problem that has been solved. However, it has been achieved, and it's there. It has been peer reviewed, and it has been checked by scientific committees at different level. At least according to me, I think there is no controversy on the scientific part. On the applications part, of course, we're very far from doing anything useful with the current devices. Of course, there is a lot of controversy. If you're interested in gossip and stuff, you can read. IBM said, yes, if the algorithms were optimized, it would take longer. It would take 10,000 years. However, that's not the key thing, because adding more qubits just makes it exponentially harder. So I think quantum is here to stay. IBM is doing a lot of work as well. They have their own. We're also collaborating here in the US. They have some labs, chips online, and I think it's a neck-to-neck race. That's for sure. Just one slide. What is quantum supremacy? Quantum supremacy is just mathematical problem, as I said. It's a minimum viability test for quantum computing. You perform a random computation, and then you check it with your supercomputer. So you design a circuit. This is your number of qubits. This is the time and the depth of the circuit. You put gates in a random way, in a certain random way, basically. You let the circuit evolve. Then you compute your output quantum state on a classical computer. You input the gates, and you're trying to get out this quantum state classically, and you compare that to what your quantum experiment gives you. And then you measure basic bit strings. You measure the output bit strings that the machine spits out, and you make some tests, some mathematical tests, and you compare. Now, that's very rough, the idea. I don't want to go into much at the moment. The issue was that when you get into a large circuit in this around 53 qubits in 2 dimensions, the supercomputer cannot keep up. It just runs out of memory. So if you want to see some sort of requirements and time scales, this is the number of qubits in the quantum experiment. This is the number of circles, how deep the circuit is, how many layers. And if you go up, down here is the classical tractable regime. This is how much time it takes you to simulate that. If you have classical n cores, like thousands of cores, and n is the number of qubits, m is how deep the circuit is, how many layers you have. As you go up, and this is the energy as well that you need to do. So if you have 50 qubits or 53, and then as soon as you start getting deeper and deeper in the circuit, it gets harder and harder. 1 minute, 1 hour, 10 years, 1,000 years, 10,000 years. So this is where the experiment happened, basically. There was around 53 qubits, and they went up to 20 cycles deep. Of course, we didn't wait for 10,000 years to do it. It was extrapolated according to the behavior further down. Again, this is a mathematical problem. It doesn't have any real application at the moment, and this is exactly where the big questions are. Using these next devices, using this prototype noisy quantum computers to take it to the next step and solve either a chemistry problem or an optimization problem or anything in that direction. And I will end with this kind of world race, the funding and the state of the art. I guess you probably knew it already, but it's quite clear there's a lot of interest in the field, also from governments and institutions and private companies. There's a flagship program in Europe. There is a big quantum initiative in the US. A few billion euros or dollars, especially for a basic research field such as quantum computing, is much more than it used to be in the past. UK has a dedicated program. This is twice as much recently. They doubled it. China is coming in very strong with many centers and many different efforts. Japan, Canada, in Singapore, we had a center for 10 years. There's discussions to go to the next level as well and push it. This is one of the top centers in Southeast Asia. There's a lot of competition, of course, coming up. Australia, Russia is coming in, and many others. Now, there's also a lot of activities in the private world. If you go back to 2012, there was only 1 or 2 companies. We mentioned them a bit earlier. Now there is a lot of software and consulting companies. We have a few in CQT as well. Then including our group, we're interested in providing consulting and advice and software developing. Of course, there is a lot of hardware companies these days. And what's very interesting is that there's also non-IT companies like Airbus and BMW and Siemens that are getting interested into this. This is good. This is, I think it's a good sign. We have to be careful because there's a lot of things to cover, as I said already. We're not there yet. We don't have the hardware yet, but I believe that it's important to discuss and interact academia and industry and see how to take the field to the next level without avoiding any hype or any bubble. And where's the hardware? How to build a device? This. I will end with this. As I mentioned, there are many prototype quantum computers out there, a few dozen of qubits at different levels of control. This is how it looks in the lab. You have these fridges. You use liquid helium to cool the chips. You put your device down here at the bottom. The chip is sitting. You can kind of parallel this with 1950s quantum computers. ENIAC was one early quantum computer of around 20 by 40 room. It weighed 30 tons. It used 80,000 vacuum tubes, and it could do 500 flops. At that time, it was a very fast machine. I mean, to calculate, to use humans to do calculations at 500 flops, it was pretty hard. You needed an army of calculators, of people. If you compare that to what we are now, of course, there's a big difference. And this goes to the question on the size as well, how we went then from that to integrate the circuits. We needed the quantum transistor. We invented the transistor, like semiconductor physics. We're in a similar area. We have these massive machines that can do certain things, and they will do more. But of course, there is a long way to go. There are different technologies still at this experimental level. We don't know which one will work. At the hardware level, we have trapped ions and superconducting qubits for computing, kind of leading the race. For other quantum technologies, there are also other things. Linear optics also is coming up in the quantum computing race. There's some new companies raising a lot of money, PsyQ and others going in that direction. The idea is to go from control and configurability at this direction, go right in this axis, i.e. increase the number of qubits, or starting from here, go up and increase the control. Here's neutral atoms, NV centers, quantum dots. There is a lot of different efforts. There's a lot of announcements and a lot of media hype sometimes. The demonstrated qubits are between 20 and 53 qubits. 53 was the supremacy. Around 20 or so are where the real quantum algorithms have been demonstrated. And there's definitely a lot of interest and the race going on. This is how a lab looks like. This is some of our labs here in Singapore. We're still, as you see, at very kind of complicated atomic physics or superconducting physics experiments. However, you know, this is there's no physical reason why this should not work. Once we get it to work, we'll find a way to get it to integrate. This is another experiment here with lasers and cold atoms. And how you do that, you send, let's say, a laser, you have your cold atoms trapped. These are ions in this case. You can read and write the internal state of a qubit by sending specific laser pulses. You can create superpositions. You can initialize the states, and you can do your computation this way. This is another lab with superconducting qubits, and the computer sits in here. All these are control electronics. And as I said, there is a race going on. Google has kind of promised to do this 3-4 years ago. They said 2 years. It took them 3-4 years, but it has happened. Lots of different groups and people are publishing at different directions. Both Europe and US and Asia is coming up as well. There are a lot of new languages, higher level languages being developed. There's a lot of collaborations between industry and academia, including ours a couple of years ago, 3 years ago, on this quantum simulation for material science. And as I said, the $1 billion or Nobel Prize question is the next 5 years, solve any useful problem at any of these areas in AI, in drug design, material design, financial modeling, chemistry, machine learning, and others using a quantum computer and making an impact. We need to kind of figure that out. And I think I'll end here. Thank you for your audience, and happy to, if you have follow-up questions, just email us. And we also have some industry collaborations and so on if you're down there or also at the high level.
Yes. So very, very good insights on the quantum computing, and the users are really appreciating this talk. I can see it already.
Thank you, Sandeep.
Feedback. And so I'll just read out a couple of questions. And one of the questions that came earlier, what is quantum version of logic gates? I think some part of it was discussed. If you want to take it.
Yeah, I can say a few more things. Yeah. So let me go back to that slide. So for example, these are some of the gates. The gates are matrices basically acting. I didn't have time to explain too much. There are matrices acting on the qubit. This 1, 0 is the qubit. In this case, is qubit 0 pointing in this direction. They live in this 2-dimensional space. And when you act with this, the qubit goes into the superposition 0 plus 1, for example. There are many of them. This is the X, the Y gates, and so on. Some of them have one-to-one mapping on classical, but most are actually not possible in classical. Because by default, the qubit lives in a much bigger space than a classical bit.
Great. And there was a question that will it be possible to get the list of resources that people would like to read from?
Yes, I mean, there are many. I can recommend Nielsen and Chuang's book for people that are, let me put it in the chat. It's a classic book, Nielsen and Chuang, Quantum Computing and Quantum Simulation. Then the IBM-Q tutorials. If you just Google to IBM-Q, you will find a lot of material online, and you can get an account there and play with it. They can look at our Quantum Lab website, the CQT website. We have a lot of output material there. I mentioned it earlier. If you go to Center for Quantum Technologies, there's a lot of articles and outreach. I would suggest start from CQT website. There's a lot of resources there.
Great. That'll be useful. And I've shared your comments. I'll just share the remaining ones also with the YouTube chat. And wonderful. Now the other question was that. All right, so I think that is already answered. Question was that is quantum computing possible on room temperature? Right now, all the prototypes are on millikelvin. Yes, I think when you were talking about.
Yeah, most quantum computers operate in very low temperatures. There are some efforts to do quantum computing in higher temperatures in these centers. And photonic quantum computers work at higher temperatures as well. So there are there as well. They are neck to neck. Superconducting and ions are leading, but photonic quantum computers are there as well. And nobody knows exactly what will happen. And photonic work on room temperature.
Great. One question from somebody who is doing, I think, research. So question is that do someone really need a PhD level maths or physics knowledge to learn quantum computing?
It depends. Quantum computing is very big. If you want to design new quantum algorithms and contribute to the very big questions in the field, yes, you have to dive deep and if not, the PhD, definitely, an arrayship or a long internship with a corresponding group. It depends where you come from, your background as well. Like if you're a physicist or a computer scientist. If you're a computer scientist, there are entry points as well in the programming languages these days, and also on the open fundamental computational science problems, like figuring out complexity theory questions for quantum algorithms. Um, it depends what you want to do. The field is growing and is getting bigger and bigger. So far, it was more demanding. You had to learn a lot of quantum physics. It's getting a bit easier to start now with these programming languages. But again, it depends what your end objective is.
Okay. So other question is very interesting, and I am also curious. So the the way we usually measure the complexity is like usually the big O notation and so on. With the new set of logic, will the complexity also change, or the law? I mean, from the mathematical perspective, it is very obvious to me that the complexity would remain the same of the algorithm. But if we are going to recode it or we are going to restructure our logic, will the complexity of the
Yes.
algorithm?
This is a good question, and it's actually yes. The quantum complexity classes is where the boundaries are. This is the open question. For example, factoring, we knew that we don't have a classical algorithm. We believe it doesn't exist. It has not been proven yet. It's an open question in the field, but people have been trying for many years. I could not find a polynomial algorithm to solve the factoring problem, what Shor is doing. Where Shor has been proven that can be do it in logarithmic time. So there's a lot of active work there, and this is for people from computer science background, fundamental complexity theory, computer science background, very many open questions there. So very exciting. Yeah.
So in quantum computing, though most of the focus is on the ability to compute, right? And then there is other areas like storage and transmission. So will there be changes or improvements in the storages and the transmission using the quantum computing?
There are many, if I understand well the question, there are many branches. I didn't talk about the other branches of quantum technology so far. Let me see, I have a slide somewhere. Give me a second. There is, I don't have it here. I mean, there is, quantum computers are expected to break crypto systems. So that kind of forced us to think how to communicate information in a secure way. Because if the internet, as we know it, if transporting information cryptography collapses, we have to find new ways. And quantum communication, quantum cryptography is a parallel discipline that's being evolved, how to do secure storage of classical information and transport it. And that's going also it's actually even more advanced, I would say, from the technical and technology side than quantum computers. It requires less resources. We use fibers, for example, or even satellites, free space quantum cryptography. CQT is also very active on that. We have a satellite program to do those things. So that's one part of the answer. The other part on the computing side, yes, we have to figure out how to connect quantum computers as well, how to make them talk to each other. And this is the notion of the quantum internet, where you have distributed quantum devices in different parts of your lab or your country or your world, and you want to get them connected. And there is a lot of work in that direction as well.
Wonderful. So there are a few more questions, and I think so. So that was basically another similar question. I think that you just answered was that the IoT applications and the other mechanisms. So I think it comes in the same bucket. Basically, the quantum computing, yes, would be used for IoT application because as the quantum computing become faster and the transmission is also impacted. So yes, it would contribute to the IoT application. Next question was how topological materials help in the development in quantum computers.
That's a very good question as well. Topological, again, very deep physics here, very important fundamental physics going on, theory and experimentally, are expected. I didn't talk about topological quantum computing, but it's also an active direction in the sense that if we can make a topological qubit, if we can show that we can make one, then that's protected against noise because of topology physics, basically topological physics. And we are looking for that for some time, also in pure physics areas like condensed matter physics, Majorana physics, solid state physics. The application in quantum computing, I was there for almost 20 years ago, the topological quantum computing approach, it was very exciting. However, we still have not seen it. It's a challenge yet. It has not been excluded. People have seen signs of it. If it works, it will be great. If there is definitely, so the answer, the short answer is yes, there is a lot of connection to that. There's a lot of topological theory for quantum computing. However, we don't have an operating, even prototype device at the moment.
Okay. So another question is that the way we have distributed computing, like we can connect computers and divide the work. And question is that can we combine clusters of quantum computers? And I can put like a couple of more additional words to this from my side. My understanding is that when you have lots of computers, normally the big data processing was invented because normal computers were not able to solve huge problems, and therefore the distributed computing came into play. The question is that my first question is, will there be a need of clustering quantum computers? Second is, will it be possible to cluster quantum computers in the same way?
Yeah, well, there will probably be a need, and this is already something that this goes to the previous question of connecting and communicating between quantum computers. Quite possibly, it won't be able to make a big device anytime soon, but we might be able to have small noisy devices of a few hundred qubits reasonably soon. And then the idea is how to get them to talk to each other via quantum links. There are strong efforts on that direction. You need to be able to figure out a basic kind of problem, how to transfer quantum information from a stationary qubit, let's say an atom or an ion I was discussing, or a superconducting qubit, which are very good to store and process information, to a photonic qubit, which is very good to transport information, quantum information. So that kind of interface at the fundamental level, the physics level, is a lot of work going on. How do I get my ion trap quantum computer or superconducting quantum computer to transport the encoding information over a fiber, let's say, to the other side of the town or the country, or via satellites between continents, and do that efficiently? There's a lot of work on that these days.
Great. And there is a question, I think, let me just read out the question. How much of classical control theory, something that can be learned at home with no giant cooling lab, has proven to be applicable to control of the quantum bits in real physics quantum computer.
Control, yeah.
Should I read out the question?
No, it's okay. Control theory is applied, and we even have quantum control theory, which is an extension of that to operate the devices, how to optimize pulses and external signals to let's say flip a qubit optimally based on a specific implementation. Because as in this case, as I explained, the qubits are physical objects, they're atoms, they're superconducting circuits, and you change from one state to the other. How do you do that optimally? How you get them to talk to each other? There is a lot of classical control theory tools applied, extended to the quantum regime, using also quantum language like Hamiltonians and control of leakage, population leakage, and so on. So yes, there is a lot of it, mostly on the hardware side, less on the algorithmic side, but it's there.
So there are two questions on the cryptography side. These are very interesting questions, and thank you for wonderful answers the audience are really liking it. Then the question.
Good.
Question is related to cryptography. Now, I think on one of the slides you mentioned that the cryptographic algorithms could be solved faster with quantum computing. So as the quantum computing becomes more practical, will it kill the cryptography in the sense that let's say SHA-1 or MD5 checksum could be cracked, and hence the entire internet will break down, like blockchain and Bitcoin will break down because of the algorithm, because of the quantum computer becoming so powerful that it can try all computations?
It's a very good question. Again, there are many aspects of this. Classical cryptography branches like RSA cryptography and what we're using now, yes, when we have an operational quantum computer, we'll break it. So anything based on that won't be secure. And that's exactly why many banks and many governments, and for years now, not even now everybody kind of knows it, but even 20 years ago, were interested in starting looking at quantum computing. However, there are some possibilities. Quantum cryptography is the answer to that, using quantum photons to encode your signals, for example, and your keys. But there is also classical post-quantum cryptography methods, as they are called, post-quantum computers based on lattice cryptography or other approaches that, at least in the moment, we don't know how to break them with quantum computers. So there's a lot of research in that direction in post-quantum crypto sims to replace classical cryptographic approaches based on different methods. So.
Wonderful. So this was very, very useful, because as the cryptography also will have to evolve and
yes.
And okay, so I think remaining are basically application questions related to telecom, applications of quantum computer in telecom, questions related to quantum computing in agriculture and banking. I think those you have answered, so I'll skip those questions. And implementation of Shor's algorithm. Okay, so Shor's algorithm is for solving the factorial, right? Not factorial.
Factorization problem.
Factorization problem. So I think that is applicable in many checksum problems. Is it? So question is that implementation of Shor's algorithm. Any specific application as of now? Is there any application?
The Shor's algorithm structure works in other algorithms as well, more upstream algorithms, but no specific downstream applications. It's because exactly it's very challenging to implement. If we can do it, of course, we can do many things, but it's kind of far back far forward in the future how to do that. It's So the answer is not that I don't know of at the moment in terms of, there's a lot, it's useful in algorithm design, finding new algorithms which are of similar type of problems, but not in applications as far as.
Okay. So we are about to finish. Maybe a couple of more questions, and
Yeah, sure.
I wanted to ask a question. Question was that um, what's the Asia's quantum computing race, and what is the global the
That's a very
landscape?
good question. Yes, I was talking about this actually very recently in another panel discussion earlier this week. Um, there is a lot of work. I mean, CQT has, I think, been and it still is one of the main, and Singapore, one of the main quantum centers in the world, quantum computing and cryptography and sensors. Um, China is coming up very strong, and um, it's not so much a matter of money anymore. I think now that the field has opened up, um, there will be enough funding. Of course, it is a matter of funding. If you come to us and say, when I say us as CQT or as any other research institution, say, I'll fund you as big as CERN with a few $1 billion, not tens of millions, like 2 or 3 orders of magnitude of, like accelerator physics is funded, for example, would you be able to build a quantum computer? I think the answer would be, we'll give it a very strong, how to say, chance. Now, I think the field is very early in a sense of still a lot of basic science needs to be resolved, and it's very open to very important to stay open and communicate our results and publish in peer-reviewed journals and collaborate. I'm very worried about what's going on recently geopolitically with the trade wars and how that will affect the field. Um, um, I hope this is not here to stay. I mean, quantum technology will become proprietary at some point, but Asia is a very good position to compete. Europe has been traditionally very strong there from the times I'm still a part of the European research team with my work in Greece as well. UK is very strong, Germany, most countries. Of course, US traditionally. I think it's a global race, and my how to say recommendation, if you want to say this way, is stay open, train more people. And one reason I'm here with you today on the weekend is I think it's very important to make the field accessible and bigger. We need to train a workforce, a global workforce, to tackle these problems, all the way from the further down applied um, uh, directions to higher level upstream deep research that is needed. We need to do that. There is a lot of demand for that these days, and a lot of competition for people trained in quantum technologies, understanding the technology and the physics and the science behind it. And I think it's an exciting time.
So great. I think that covers most of the questions. I mean, most of the questions that are coming in, they mostly have been answered during the talk, related to cryptography, related to applications in different fields. And there is one more question I wanted to ask. So I want you to give a little bit more brief about like your group. It's very exciting times, and I personally was very impressed with the CQT and in general. And I wanted to ask, like, what exactly your group is into.
Yes, we are doing. I mean, we are involved in most of the things I've discussed today. We're doing a lot of upstream research in designing new algorithms and figuring out the nitty-gritty details down there. We have a few PhD students and postdoctoral fellows working in that direction, coming up with new ideas, and that's quite hard. You know, coming up with new algorithms is not a straightforward thing. You need a lot of training, a lot of years. But we also spend more and more time recently talking to industry players and trying to figure out what is the useful problems we can use quantum computers for when they are out. And that requires bridging the gap between industry and academia. As I say in the slide here as well, we're doing programming workshops, we do consulting, we provide sometimes possibilities for some joint R&D programs, also via my group and also via some of the spin-offs we have, which I'm also kind of involved. And we're trying to do the full stack in a sense. I think the field is evolving in all directions, and it's important to keep in touch both with the academic upstream research, but also down there at the industrial level, what is possible and how we can do it.
Okay. I had one more last question. I think we are all through.
Please go ahead.
So, do you? So there is somebody has asked this question. Question was that what are the prerequisites to get into quantum computing field? I will add to that question, asking that one, if let's say somebody has to do PhD or join your group, what will be the prerequisites from your perspective?
For academic direction, we're looking for people trained in natural sciences, physics, computer science, engineering, being very motivated and also, you know, it's a very competitive place, so they have to have proven their abilities to attack hard problems. All three areas are possible. In my group, mainly physics, but we also take computer science and engineers at times, and chemists. Then there is the whole kind of spectrum. This is what I'm talking about, PhD or masters now. But there is also possibilities to work on more applied problems if you have a machine learning background or AI background, programming, software development, programmers. These are also possibilities for more applied directions, also with the spin-offs and so on. That so there are different entry points depending what you want to do and the background of it. People can write to me and I'll try to answer with reasonable time the questions if they have. If people are listening and want to write to me, be very brief, you know, just give me a short paragraph, who you are, what your studies are, and like very basic 2-page CV and why you're motivated to join either the more applied directions or the academic direction.
Great. Wonderful. Thank you. Thank you, Professor Dimitris Angelakis. Thank you for basically imparting the knowledge to the world. And this is definitely, you know, a way of making the world a better place. Probably more people will be inclined to join and work in quantum computing. More people will learn about it, and hence the world becomes a better place as we talk.
Thank you, Sandeep. Thank you for the invitation. It was a great pleasure to chat with you, and I hope that this is useful to our audience.
It was wonderful. Lots of people appreciated it. And again, thank you very much.
Thank you. Bye-bye.